So good morning, everyone, and welcome to the almost last tutorial in our course. Today, I'm going to talk about training with multiple GPUs. So let's begin. If you can stay muted unless you have questions. Thank you. So let's begin. So why do we even want to do that? Why do we want to train with more than a single GPU? So as we saw in the GPU tutorial by NVIDIA, each GPU has many small processing units that can perform efficiently in parallel. And using more GPUs will grant us access to more such units, so we can perform more parallel operations. Another bottleneck we may encounter is GPU memory. Sometimes we cannot fit the model and the data into a single GPU card, and we need to extend the GPU memory by using multiple GPU cards. So how do we want to parallel using GPU? So we can broadly split the approaches into two types. One is model parallel and one is data parallel. And what do I mean by that? So with model parallel, we split the processing of the model to several GPUs. So we start the processing on one GPU, the blue one, and we continue the forward and the processing on another. And this is usually useful when we need more GPU memory. On the other hand, there's the data parallel approach, where we say we just split the data into the different GPUs, and we perform parallel processing of different data on different GPUs. And this is usually done when we have enough GPU memory, but we want more compute power in parallel. So let's see, let's dive deeper into these approaches. So let's start with model parallel. So sometimes the memory is not enough. So we want to process a batch, and the model, all the weights and the data simply won't fit into the memory of one card. And if you're using WAIC, this can be very rare occasion, because we have available cards with 32 gigabytes and even a few cards with 48 gigabytes of GPU RAM. But sometimes if you train very large transformers, very large graphs, you can even run out of memory for these GPUs. So we want to split the processing between different GPUs, as we said before. And how is it done? So here's a code example. And basically what we define our model, and now we explicitly partition the model into two parts. Part one with some layers and part two with other layers. And we need to take care to move the first part into the first GPU and the second part to reside on the second GPU. And in the forward pass, we take the data from the CPU to the first GPU, and then we process the first part on the first GPU. Then we need to move the data to the second GPU and process the other half. And know that the output would be on the second GPU memory. Any questions about that? Okay. So model parallel is very nice because it allows us to take advantage of GPU memory of several devices. So we are not restricted to one. We can split and work with several devices, and that's it. The problem with it is that, as you saw before, we need to tailor our code for this solution. So we need to change the way we implement our model. We need to write special code And we need to do this bookkeeping of where the tensors are, on what devices, which part of the model. So if we put the model on the first and the second devices, and then we need to take care that the data goes first to the first device and then to the second. So it's tedious. And most importantly, it puts all the burden of the coding of this bookkeeping on us. No one will do it for us. And since model parallel is not trivial and requires major rewrites to the code, we must use it. So if we can fit a very small batch into a single GPU, what we can do with a single GPU is do gradient accumulation. That is, we can accumulate the gradients of several forward passes before making an optimization step, an update to the weights. And what do I mean by that? Here's how we usually train our model. We update the weights in this optimization step after we estimated the loss function for a single batch. So after every forward and backward pass, we optimize and we change the weights. Have you ever wondered why we put this 0 grad here? With gradient accumulation, what we are doing is we zero the gradients and then partition the batch, if it's too big, into smaller sub batches. We do several forward and backward passes without updating the weights. And only after we processed all the big batch, only then we do an updates to the weights. So we accumulate the gradients from all these sub batches, and then we make the step. And this is why it's important to reset the gradients before this loop, and this takes care of gradient accumulation for us. The gradients are accumulated in the tensors inside the model. So this is a very subtle change to the code. It's agnostic to the implementation of the model. We don't need to rewrite the model like we had to do with the model parallel method. And effectively, we update the gradients based on a large batch, but we serialize the processing of this large batch into small sub batches on a single GPU. Is that gradient accumulation clear? Excellent. So this leads us to the next parallel GPU approach, which basically we are going to do this gradient accumulation, not serializing these small batches, but in parallel on different GPUs. So this requires minimal code change, and it takes time because we do it serially. So now we want to do this, taking large batch, split it into smaller chunks, and instead of processing them one after the other, we want to process them in parallel on different GPUs. So this helps us take advantage of GPU power and more GPU compute if we have many devices. So this is called DataParallel because we are parallelizing the data. And when we would like to do that, it's usually when we want to process very large batches, but in parallel. And what this requires, what the components that we need to have is we need to have identical copies of the model on the different GPUs, on the different devices. We are going to split the data into different sub batches. So we take a very large batch and partition it. We don't sample from it, but we partition it into different chunks. And we need to synchronize the updates between the two GPUs, between the instances on the different devices. Questions so far? Okay, so let's look more into the details of this data parallel paradigm. So we have two GPUs. And we start with two identical copies of the model. Each GPU has its own copy. We take one large batch that cannot fit into one GPU and divide it into different sub-batches. We can now run forward pass on each GPU and compute the loss. Note that although the loss function is the same, because we are training the same model, the loss values are different on each GPU. So L1 doesn't equal L2. Do you know why?
Because of the different parts of the batch.
Exactly, Rafael, thank you. So because we looked at different samples of the data, of the training data, so the loss value is slightly different in each and every one of the copies. So we can now compute the gradients using backward pass. And what will happen if we update the weights now?
We'll have different copies of the model on two GPUs.
Exactly, the two copies will diverge. They won't be identical. So what we need to synchronize the updates. And this entails some communication between the two GPUs, between the devices, to make sure that they are identical. And as you can see, these components are agnostic to the model and the implementation details. Therefore, PyTorch ships with boilerplate data parallel methods. And we're soon going to see them. Why it's so important to have identical copies of the model on the two GPUs? Why do we insist on it? And why do we synchronize and pay an overhead for this to be the case? So what we are doing, deep neural training, we are in optimization. We are using stochastic gradient descent to find the weights that minimize the loss function. So this is our loss function, and we want to find the weights that minimizes. So how do we do that? We do this with stochastic gradient descent. That is, we are estimating the gradients at our current position and taking a step with respect to the estimated gradient direction. But working with parallel, what we basically have, we don't have a single gradient now. We have several stochastic estimation of the gradients, but we average them and we update the weights. We can get some joint estimation from these noisy gradients. However, if we do not have identical copies, so basically we have one copy on one GPU and another copy on a different GPU, then the gradients estimated by the other device would be completely different. And we'll make steps in a completely different ways. And basically we are updating two different models. We are solving two different optimization problems. This is not joint optimization. This is not parallel processing. So this is why it's so crucial to make sure that the two models on the different devices are indeed identical. So these are the components that we need to worry about when we are doing parallel processing, data parallel processing. We make sure the copies are identical because we want to solve one optimization problem and not several different problems. We want to have single model and a single solution. And we need to worry we need to have different views of the data because otherwise we will compute the same gradients. So we'll do the same job twice, the same computation twice, instead of doing different computations and benefit from the compute power we have. And we need to worry about synchronization. But since all these components are agnostic to our implementation, we can use boilerplate code to do it for us. So let's see what PyTorch gives us. So the first and the most easy way to start with DataParallel in PyTorch is using NN DataParallel. And how does this look like in the code? So we start our model, we define it, and now we make it parallel by just wrapping it inside this DataParallel instance. And what this does, DataParallel holds basically a master copy of the model and all its weights. At each iteration, it replicates the model to all the GPUs. So making sure you have identical copies of the model everywhere. It partitions the batches from the data loader into the number of GPUs that we are using. And noted that in this case, the batch size that is defined by the data loader is the total batch size that is processed by all the GPUs. And each GPU will see a smaller portion of this batch size. And once we compute an update, the optimizer wants to update the weights. DataParallel synchronize these updates for us, take care of all this communication between the different GPUs, and make sure it has only one single synchronized master copy for itself. So what's nice about this DataParallel is that it requires almost no effort on your part as a programmer. So you just wrap it once and PyTorch does everything for you. But as you can expect, if this is a very, very general method, oops, sorry. It has some increased overhead. It doesn't give you a fully optimized code because it has this synchronizing of the entire model back and forth. It's using threads instead of processes, of independent processes, and we see that in a minute. And this makes it not very optimized in terms of runtime. So if you really want to squeeze the most of the many GPUs you got, you need to do something that is requires more effort on your part. And let's see that. This is done using distributed data parallel. Again, it's a PyTorch method, but this is a method that is more optimized but requires more effort on your part. And it requires the effort it requires translate to more changes to the code. And why is that? So distributed data parallel works not with threads, but with multi-processes. So threads are residing inside a single process. So you can think of a process as a program that's running on your computer. So you run Python once, and the threads are working on parallel to compute this program. But with multi-processes, you have different independent programs that run on the different cores of the CPU and just communicate between them to perform tasks much more rapidly. So if we previously considered only 2 GPU devices, we now need to consider also different CPU processes. Each process is associated with one of the devices. So each process sees one GPU. And the processes, unlike threads, operate as 2 independent programs on the machine. So we have the same code that we wrote running basically 2 programs on different CPU processes. And now each process fetches a different portion of the training data and processes independently, computing the loss and computing the gradients. At this point, the process uses inter-process communication to synchronize the weights between them. So before we delve slightly deeper into the details, a few technical terms that we will use and that are used when you program these distributed training, first of all, the number of GPUs or the number of independent copies of the programs that are running, it's called world size. In our case, our world size is 2 because we have 2 GPUs and 2 copies of the program that are running. And each copy has its own rank. So we have rank 0 running on the first CPU and rank 1 running on the second CPU. And rank 0 is usually treated as the master, where the synchronization happens, and this rank 0 program basically governs the optimization process, the parallel processing of the data.
I have a question.
Yes.
So when you said that you synchronize the gradients, the weights updates, so it's just like averaging the gradients between the two models?
Yes.
Thanks.
Think of it, if you have very large, it's basically you have a large batch and you compute the gradients, and what will happen if you compute the gradients in 2 times? So it's the same as we did with gradient accumulation, but just now in parallel, not one after the other.
Yeah, it's understood. I just wanted to clarify. Thanks.
Okay. And another nice thing about it is that all this synchronization is done for you either by DataParallel or by the distributed data parallel. You don't really need to worry about it, which is, I think it's a very nice property. Yes, Omer.
What about the batch statistics, like batch norm, for example?
It's not an excellent question because I don't have slides, but that's
also, like there are methods like I don't know, the SimCLR, for example, or unsupervised metrics learning stuff that really needs the batch statistics, for example. So
okay, so one way of handling batch statistic is ignore them and say, well, basically we have some statistics at each and every one of the copies, and they will slightly diverge in the forward pass, and we'll synchronize that during the backward pass, so in the synchronization stage. And then in that case, you will have different results if you're running in parallel and if you're running the entire batch on a single device. Another option is PyTorch also has a synchronized batch norm layer, and it has some functionality that you can replace all your batch norms quite easily with a batch norm that supports this synchronization. I didn't get into these details here, but it requires a few more lines of codes, but it's basically done for you. You don't need to worry about that, but you need to know that you want it and that you need to do it. But if you go to PyTorch documentation, you'll see synchronized batch norm and what to do with it. Okay, but yeah. So how does the code look like? So first of all, we have this program that runs on all the different processes. So we have this single function that each process runs a copy of this function. So what we have here, so the function gets the rank to know on which of the GPUs on each of these instances it runs, and gets all the arguments it needed. So first of all, we init the context of this process. So this process needs to know that it's not running independently, it's not alone in the world. There is a bigger world size and your rank within it. So you need to wait for the other processes to start. You need to know with which processes you communicate. So you can have this init method. So basically listen to a port, some random port on your machine for all the other processes. And usually the rank 0 process is the one that does this synchronization. So you don't need to worry about it. It's just a PyTorch code that tells your program that it's not alone in the world, but it's part of something bigger, and it needs to take that into consideration. And this has to be done very early on the program. You can't use other distributed commands before you make sure you know your place in this context. Again, we wrap the model. So instead of just data parallel, we now have this distributed data parallel around the model. And what is the device we are running on? And it's very important to note that since distributed data parallel doesn't synchronize the entire model like in data parallel, so it doesn't ship the entire model every time to all the GPUs, it only synchronizes the updates. The model must be initialized before you call data distributed. So in order to have this same identical copies on all the machines, it must be initialized before calling distributed data parallel. Another thing you need to worry about is how to read different parts of the training data. So with data parallel, we read the entire data because we work on threads that communicated on a shared memory. Now each program runs independent of the other. It needs to read an independent different part of the training set. For this end, we have a distributed data sampler that gets the entire training set, the world size, and our part in it. And now it knows how to sample different portions of the data for each and every one of the processes. So it won't, so if we weren't to use that, so all the processes would sample the same batches and would have all the different GPUs processing the same data. So this code is basically invoked world size times 2 in our case, 1 on each and every one of the processes. But we don't really explicitly need to call it this time of processes. This is what the main function does. And we have a main function that in it, the argument, whatever it does, and then it spawns, it basically triggers the call to the function training world size times with the arguments. So in terms of the flow of the code on the machine, it doesn't just go to train here and start executing train. Instead, it starts new programs on each and every one of the processes, and each and every one of these programs will run this code. Okay, so this is different than a regular Python when Python calls a function. It basically stays in the same context. This opens new context on different processes and start this train. And basically, spawn tells each and every one of these instances what is its rank. So the rank the train got, it gets it from the spawn function and all the rest of the arguments. Any questions on that? Okay.
Shai?
Yeah.
The update of weights, in which function do it?
So you don't need to worry about it. So basically, once you construct these distributed components, the optimizer just do a step, and the distributed data parallel knows how to synchronize things for you. So
Yes,
I
but
really
what
don't know
I'm
how it's
asking,
implemented.
Where is the for loop on the batches?
So, okay, so it's the same. So you have the loader here. So the difference here is that you don't shuffle, you just provide it with the sampler, and then you run on the batches.
Okay.
Now, the fact that you're using this sampler means that if you have 1,000 large batches in your data set, and That's tricky. So basically, if you had single GPU and you needed 1,000 iterations for an epoch, now you're using two GPUs, you only need 500 iterations. So if you go through the data loader, the sampler will only sample half the data. So one epoch would consist of 500 iterations.
And the for loop of epochs is in the main, right?
Yes, yes. You still need to do this epoch loop.
But it's in the main function, so that in the train.
No, it's not in the main function. The main function just call the train. So if you want to do this, to do several epochs, so each and every one of the process need to do these several epochs. So the main function start, you can think of this train function as what you are now using as the main function that does the training, the validation over epochs, etc.
Okay.
Okay, so the function train, it's basically the very same code runs on all ranks, all the instances. What does it mean? What happens if we have a print command in our train function? How many prints will we see on the screen? If our word size is 2. So basically, if we want to just to print hello world, we'll see 2 hello worlds on the screen because we have 2 independent copies of the program running. Each copy has its command print hello world. So we'll see 2 prints on the screen. So to avoid this, it is customary to do all these printing or logging to TensorBoard or to weights and biases, etc., only from the rank 0 process. So we know each process know its rank. So only if you are at rank 0, do the printing or do the writing to TensorBoard. And regarding evaluation, so since evaluation doesn't entail heavy processing, it's a smaller set, it doesn't require gradients, and it's usually faster. Usually people don't do it on parallel and just do the evaluation on the rank 0 instance once every epoch or as you choose. And if you do want to do the evaluation in parallel, you need to take care of synchronizing the accuracy between the different instances. This is not done for you because DataParallel only cares about updating the gradients. And since gradients are not updated during validation, the distributed data parallel won't help you to parallelize validation. Okay? So to recap, instead of using threads that has shared memory and can bother each other in runtime, that what DataParallel did, in distributed data parallel, we are using, we spawn world size number of processes, independent instances of the same code. And each process handles different part of the training data. And distributed data parallel does all the synchronizations for us. So to recap, we saw 2 ways to data parallel in PyTorch. One is data parallel, which is very easy to use, and the one distributed data parallel. With data parallel, we only need to wrap the model, and it's very easy, and we have thread level parallelization. But this comes with a cost of increased overhead. So the performance we get if we use 2 GPUs is not twice as using 1, but just slightly higher than x1, but not x2 factor in runtime. In distributed data parallel, we need to work harder. So we need to write this process code that runs in each and every one of these instances. We need to write this thin main function that spawns these independent programs. We need to init the processes to establish connection between all the processes. We need to sample data in a distributed aware manner. And we use data distributed to synchronize the model. However, once we have this in place, we made these changes, we get significant speed up. It's probably even for a single machine with many GPUs. But more importantly, or I don't know, it can scale very easily to multiple machines. So now these different processes don't have to run on the same node. They theoretically can run on different nodes and communicate between them. And it also allows for flexible parallel scenarios, like doing some model parallel between different instances. But we don't cover this. And in fact, WAIC doesn't really allow you for the moment to do this parallelization across different nodes. So we're only talking about different GPUs on the same machine. And if we speak about WAIC, if you want to have more than a single GPU, so you submit your job and ask for more than one GPU. You can ask for 2, up to 8. Currently, we have servers with 8 GPUs. You can no longer use the long queue because we don't want you to take many GPUs for a very long time. So you can use either medium, I think, for 2 GPUs. And if you want more than 2 GPUs, you'll have to use the short queue, so for shorter times. But once you get a GPU, you can ask for more GPU memory and for more threads. So right now, we roughly allocate, so there's roughly 64 GB of CPU RAM for each GPU on the machine and roughly 10 threads for GPU. And once you ask for this, you can run NVIDIA SMI and see that you got 2 GPUs for your process, for your job. So note that it's harder to schedule jobs that ask for many GPUs because usually if the cluster is very busy, you'll get slots available that are 1 GPU size. And if you ask for 2, you'll have to wait longer. And be kind to your friends because we are all using the same GPUs. Don't ask for many GPUs if you don't really have to. So don't use resources beyond what you need. Any questions? Great. So before we leave, so we can wrap our models in DataParallel or distributed data parallel. We get more GPUs and we are happy. So do we really want to do that? So does it really, if now the cluster is available, can we just ask for as many GPUs as we want and just speed up our training? Well, so in terms of images per second, people report with a very large number of GPUs. If you have powerful communication between the machines, between the nodes, and between the GPUs, basically you can scale almost linearly with the number of GPUs. So yes, if you have more GPUs, you can theoretically pay very, very low overhead and process more images per second, more training data per second. So this is very nice. You can go through the training data set very fast. So these graphs are for a specific HPC cluster, but we also did some similar benchmarks on WAIC, and we saw similar behavior as well, especially if you're not leaving the boundaries of your node. We have very fast interconnect hardware between the different cards, GPU cards on the same machines. So basically, you can scale and pay very little overhead. So if we can process, we can go through the data with very large batches, we can go through the training data very fast. Do we need fewer iterations to converge? Do we need less epochs? Do we need less training time? Sadly, it seems like that's not exactly the case. So depending on the model and the task, so these are different graphs for different models, different tasks, but they are asking ourselves, how long does it take to train for reaching some validation goal? And as you can see, usually it starts scaling linearly with the batch size. So as we increase the batch size, indeed, we need shorter times, but it doesn't go all the way for very large batches. So at some point, and it's a different point for different models and different tasks, but the graph just flattens. It won't help you if you train on very, very large batches. So you'll consume a lot of compute resources, but you won't get the benefit, won't scale linearly at some point. So in terms of steps for convergence, this is not a very good news. So, okay, we are willing to do this, to pay this cost, and we want to train our model until they converge. Does the quality of the training remain the same? So does increasing the batch size affect the model to which we converge? Do we get a better model or a similar model in terms of generalization of this model, which is basically what we really care about? So if we naively only increase the batch size, we get to the roughly same training error. As you can see here, all these different graphs represent different batch sizes. And in terms of training error, they converge basically to the same point, the same output training error. However, if we look at the validation error and the generalization capabilities of these different models, we'll see there's quite a gap between the model that trained with very large batch to those trained with small batches in terms of generalization error. So we converge to roughly the same training error, but we converge to a different point in this space of different models. And this point is not very good. It doesn't generalize very well. So basically what it means that if we increase the batch size, we might be able to train faster, we might be able to train in a more efficient way, but we are not doing a very good job in terms of generalization. And why is that? Well, using large batches provide better estimation of the gradients because we have less sampling noise in the estimation. This in turn allows us to compute and do a more accurate exploration of this loss space and converge to a more accurate point. So let's recall what we saw on the fourth lecture of this course. So if this is, for example, our training loss function, using gradients, noisy gradients resulting from small batch size would usually won't enable us to find this sharp local minima because it's very difficult to find. We need to be very close to it and be very accurate about it. So we need to make sure we are not estimating the gradient wrong and jumping outside of it. But if we are using very accurate gradients, we'll probably find this sharp minima. So is it good for us to find this sharp minima? So the test loss, which is what we really care about, is similar to the training loss, but it's not exactly the same because it's estimated using slightly different examples. So it's roughly the same, but not exactly. And what happens if we converge to this sharp point? The deviation from the actual test loss is quite large. So even a small change between the train and the test loss entails a very large test error, very poor generalization. Whereas if we are here at this shallow local minima, the difference is not that critical. So we see that we want to find these wider and more stable minimas for robust generalization. And this is usually, we achieve this using small batches and noisy gradients. So what happens if we have large batches? Basically, we have smoother gradients, we have more accurate estimation, and since we don't want to get stuck in these very sharp minima, we want to increase the learning rate. We want to make larger steps to compensate for these accuracies so that we won't be falling into these sharp pits. However, this is nice when we do some minor increase in the batch size and minor increase in the learning rate, but if we increase the learning rate very much because we increase the batch size very much, now we run into problems of optimization instability. If we optimize with very large learning rate, as we saw on the first lecture, we can encounter instabilities in the optimization process. So what can we do? We need to use a variant of stochastic gradient descent that is tuned for working with very large batches, that it knows how to use this large step size without getting into instabilities. One such optimizer was proposed in this work. It's called Lars. And basically what it does some adaptation of the learning rate for each and every one of the layers. So it's not like SGD that has single learning rate for all the weights. And it's not like Adam that has like adaptation for each and every one of the parameters, but it's somewhere in the middle, and they showed in their work that they are being able to get good generalization, even working with very large batches. So to conclude, there's nothing stopping you from training with multiple GPUs, but you need to be aware of the indirect effects this may have on your optimization and how to overcome these pitfalls. So let's recap. We want to use parallel GPUs when we need more compute power or we need more GPU memories. If we need more GPU memory, then usually what we'll do model parallel. We'll split our model between different devices and just go one after the other. It requires some code changes to the model. It requires some bookkeeping on our part. If we want someone else to do the job for us, so we do data parallel. We take advantage of more compute power processors on the different GPUs by parallelizing the processing of a single batch. And this is a boilerplate and it has ready-made in PyTorch, either DataParallel, which is very easy to use, or the distributed DataParallel that requires some effort on our part, but we will be rewarded by better performance. And if you don't want to do parallel, but you are stuck with small memory, you can also always do gradient accumulation when you don't have many GPUs available. And always remember, with great batches comes great responsibility. Any questions? Okay, so just a few